Let's track a moving object. As it accelerates along the path, its changing position is plotted against time. Notice this parabolic curve. It perfectly visualizes increasing velocity. Now, let's track the velocity. Because our object is accelerating at a constant rate, the velocity increases steadily, giving us a perfect straight line. But here is the most crucial concept in kinematics. The area trapped under a velocity-time graph exactly equals the total displacement. Now, what if the object already had an initial velocity? The graph starts higher up. To find the total displacement, we just split the area into two simple shapes, a rectangle and a triangle. The rectangle's area is v sub 0 times t, and the triangle's area is 1/2 a t squared. Add them together, and you've just visually derived the most intimidating kinematics equation. Now, let's move to the acceleration time graph. Since our velocity was increasing at a constant rate, the acceleration is just a flat, horizontal line. And here is the trick: the shaded area under this graph gives us the exact change in velocity. So, if the area under an acceleration time graph is the change in velocity, we can write this mathematically as delta v equals a times t. But a change in velocity is just the final velocity, minus the initial velocity. Rearrange this, and we get our very first kinematics equation. In free fall, notice how the velocity changes, but gravity always points straight down. You don't need to memorize new equations for free fall. Just take our general kinematic equations, change acceleration a to negative g, and swap x for y. And just like that, you have your vertical motion equations. How do we find the maximum height? At the very top of its path, the ball briefly stops, so vertical velocity is 0. Plug 0 into our third equation and solve for displacement. And we get our formula for max height. Next up, we'll dive into projectile motion. Subscribe so you don't miss out.